Hello and welcome to our today's webinar about the application of CFD for the design of hospitals. My name is Milad Mafi and I'm very glad to see that so many people joined today to learn about the possibilities CFD provides you with for AEC industry with a focus on hospitals. And it's a big pleasure for me that today Alireza Kamani from Verist Engineering will join and provide us with some very interesting insights. And before we start to take a look at our today's agenda, I would like to quickly introduce myself. My name is Milad. I'm a product marketing manager here at SimScale. I've studied mechanical engineering with a focus on simulation and biomedical engineering. And as a part of my role at SimScale, I'm organizing webinars and workshops which helps interested users, professional students to get started with simulation and CFD. And today with me, as I mentioned, is Alireza Kamani. He is the senior engineer at Verist Engineering. Alireza holds a PhD in computational fluid dynamics from the Johns Hopkins University and a Master of Science in Structural Engineering from the University of Tehran. And he has a huge experience with consulting and CFD, FEA, conjugated heat transfer, and all other disciplines of simulation. And as part of his role at Verist Engineering, he is leading consulting projects for other companies. And later, as I mentioned, he will show us some of his very interesting work. But first things first, now let's take a quick look at our today's agenda. And basically, we have 4 big sections. And at the beginning of the webinar, I will introduce you quickly to SimScale. So we will talk about what simulation actually is what cloud-based simulation is and also how cloud computing can help to make simulation more accessible. After that, we will quickly talk about some aspects of CFD and with a focus on using CFD for designing mechanical ventilation concepts. And after that, as I mentioned, Alireza will take over and present you a very interesting case study where they use CFD to optimize the airflow inside a surgery room. And finally, we have a Q&A. So in the case you have questions related to my part of the presentation or to Alireza's, just write them into our question toolbox and we will try to answer the questions during the webinar or at the end during the Q&A. All right, so let's start. And first of all, I would like to talk with you a little bit about SimScale and about our vision of democratizing simulation. And we have a lot of registrants today and attendees, and I'm quite sure everybody has a different background. However, you registered for that webinar, which means you're interested in simulation. And as you might know, simulation is actually a quite old technology which was developed in the middle of the last century and got adopted in the last 30-40 years in a lot of industries. And today, simulation is a standard in some industries like the automotive industry or the aerospace industry. However, still 95% of engineers have no access to simulation tools at all. And this has a lot of reasons. And basically, to put it in a nutshell, simulation on the one hand provides us with a lot of great advantages, but on the other hand, traditional simulation solutions come with a lot of initial costs for getting the hardware, getting the license, which means you need to pay a huge initial investment before using simulation. And that's the reason why simulation was not used in majority of engineering companies in the past. And that's exactly where SimScale starts. SimScale was founded 5 years ago as a spin-off from the Technical University of Munich, one of the leading universities in Western Europe. And back then, the idea was to create a simulation platform which is accessible for every engineer in the world. And basically that's SimScale. So SimScale is the world's first web and cloud-based simulation platform, which means you can easily test and optimize your product designs without building a prototype in your web browser. And I know that there's a bunch of simulation tools available there, and a lot of them are also for free. So why should you consider using SimScale? Well, the first thing which is so special about SimScale is actually the pricing model. And actually SimScale is free, so everybody can create a free community account and simulate as much as or she wants. And the only thing is that this price model has basically two sides. One is what we call community, which is free, and all community projects are public. But we also offer professional plans for commercial use, where you actually can scale how much you want to spend for simulation, and you only need to pay what you need. But besides of that, SimScale is an all-in-one simulation platform, which means it's not only limited to CFD, which we're going to talk about today, but you can also perform structural simulation and thermodynamic simulations. Since it's cloud-based, you don't need to buy any hardware or software. Actually, you can use it on any device, and it will massively accelerate your simulation process, since you can run your simulation up to 96 cores. And also what is very interesting is our completely new support and collaboration approach, which means, first of all, the SimScale platform is really connected with our support, and you can reach out to the support using chat, phone, and email. And SimScale, on the same time, is a big community of more than 120,000 engineers which are interested in simulation, and therefore it's a great place to get started by using public projects, for example, or talk to people inside our community. And as I mentioned, simulation is mainly used in the automotive and aerospace industry. However, the adoption is also increased in other industries. And one industry which is rapidly growing is the so-called AEC industry, so everything related to architecture, engineering, and construction. And just to give you an overview how CFD can be leveraged for that, let's quickly take a look at that slide and discuss some different applications. And the one application which is used heavily by our customers and users is to use fluid flow simulation to validate the design of HVAC system and its parts. So whenever it comes to design, let's say, single segments, ductings, etc., CFD is really great because it allows you to really precisely predict pressure losses, flow homogeneity, and some other important aspects. But it's not only limited to the systems, let's say, inside the building. You can also use it for predicting, for example, wind loads, and to understand the interaction between the wind and your building shape. And usually when you have very large buildings, you need to do wind tunnel testing to show, and this, by the way, is based on the National Building Code, to show that your house will withstand, let's say, high wind loads and forces. And instead of building a wind tunnel model and running a wind tunnel test, which is very expensive, you can use CFD just to do this test virtually. Yes, and there are some other things we can do, especially when it comes to improving energy efficiency or optimizing thermal comfort. Usually you can basically do these two things at the same time. So you can use CFD to find a better design which will increase the comfort and at the same time which needs less energy. And we're not only limited to thermal things, but we can also like simulate and consider air quality and the transport of particles and other substances. And before I give the word to Ali Reza, let's quickly discuss and try to understand what and how I can model mechanical ventilation problems using simulation. So usually independent from what we are simulating, if it's a hospital or a residential building, is a general structure every simulation follows. So, and basically we can divide it into two things. One is modeling the domain of your fluid, and the other is to choose the right boundary conditions. So when it comes to domain modeling, actually there are three different categories of parts of your domain. First of all, you have the overall domain, and just to make sure you get it right, we're talking about the fluid domain. So we are interested in the region which is enclosed by the walls. And first of all, this domain can interact with an environment, and we can supply fresh air through supplies and remove it through the exhaust. And when we bring in new air, this means we bring in new mass and new energy. And also inside our domain, we can have some interactions, and this is what we call obstructions. And basically, everything which is somehow interacting with the flow is an obstruction. So in the case of a hospital, it can be the bed. If you're talking about residential building, it's the furniture and some walls, etc. And basically, every simulation where you want to simulate mechanical ventilation using CFD, you use these three things: inlets, outlets, and obstructions. And another aspect which is very important is how we can model our problem. And basically there is three kind of boundary conditions which we can use. The first is about the flow conditions, and this includes the velocity and the pressure. So if we have a supply or an inlet, we can define, for example, the pressure gradient or the velocity of the air entering the room, and the same for the outlets. And something we can also consider are thermal conditions. And actually, there are three things we can do. We can take a look or consider what happens if we have a defined temperature, for example, on a surface. But we can also define the thermal conditions by defining the heat generation or the heat transfer. And the third thing we can do is to investigate the movement of passive scalars or passive parts inside the flow, which is interesting when it comes to contamination. And this can also be considered using SimScale and the modeling strategies for mechanical ventilation. Finally, before I hand over to Ali Reza, I would like to show you quickly what does it mean in reality, to give you a little bit more vivid picture. And actually, whenever we do a simulation with SimScale, we have three steps. The first step is to import your CAD model. And at SimScale, you can actually just upload your CAD model. We support a lot of different file formats, including native formats like SolidWorks or Rhino, as well as Exchange data formats like STEP, IHS, and STL. And usually you need to prepare your geometry a little bit in your CAD system, make sure it's watertight and some other things, and then you can import your CAD model and start to set up the simulation. And this includes a step we call meshing, and this is basically dividing your flow domain into a lot of small elements, and later we will only calculate the flow variables like pressure, velocity, temperature for the center of each of the cells. And in the end of the day, the resolution of our mesh is related to the local accuracy of the simulation. And after the meshing, you start to define boundary conditions and do the actual simulation setup, like what is the inlet, what is the outlet, what are the temperatures inside the room, etc. And then you can just run the simulation. It will be very quick, since everything is performed on the cloud using a massive amount of CPUs and computers. And once the simulation is finished, you will get notified, and you can visualize the simulation results in your in your web browser, or download them for further investigation. And based on these results, then usually you will modify the design and improve it. And just to show it, so this is a simulation project I created on SimScale, and as you can see, everything I do is happening in the web browser. And so this is the project. As you can see, we have two different designs. one mesh, one simulation, and then we can just open the project. And as I discussed in the first step, you import your CAD model. In this case, it was imported as a step file. And this is a hospital room, and here you can see the rooms, the walls, and the obstructions inside. Then the next step is to mesh this. And here we have a lot of different meshing algorithms. A lot of them are working fully automatic. And as you can see, we refine the mesh in those areas where we expect to have high changes, high gradients, and we can make it more coarse where we think the gradients will be smaller. And once the meshing is finished, you just go in simulation setup. You need to choose in the first step what you want to simulate, in our case conjugated heat transfer. Then you define like the gravity, what is the material, in our case air. We can just import the material properties from our material library. And then you can define different boundary conditions like the inlet here, walls, it's another wall, but the difference here is that we have different temperatures in the walls, and so on. Yes, and finally, you just create a new run. And as you can see, the simulation was just calculated in 13 minutes. And the final step is doing the post-processing, which means we can visualize the simulation results in our web browser. All right. I hope this was a good introduction, and now I'm very happy to give the word to Ali Reza, who has prepared a case study and who will show us how various engineering is using CFD to optimize different projects based on the example of a hospital room. Ali Reza, can you hear me?
Yep, thanks Milad. So let me share my screen and let me open the presentation. So I'm going to talk about using computational fluid dynamics, CFD, to simulate airflow in a hospital room. Before going to the presentation, I want to give you a little background about our company, Veris Engineering. We are located in USA, Massachusetts, and we do a lot of analysis using different simulation codes. Here are 6 examples that I thought might be relevant for this webinar. I will show them to you in this slide and the next slide. The one on the left is a LED cooling problem. It's a conjugate heat transfer problem, meaning that it involves heat transfer and fluid flow. Beside that is RF tissue ablation problem that involves electric field, heat transfer, and fluid flow. And then the one next to it is a golf ball impact problem where the focus was on the nonlinear material behavior of the ball. Then in the next slide, I have on the left an acoustic particle focusing application where we use acoustic phoresis forces to move particles and concentrate them in a channel. This has application in biomedical devices. The next one is peristaltic pump, which is a fluid structure interaction. And finally, this one is infant incubator problem, which is airflow with heat transfer analysis, similar to what I'm going to talk in the next few slides, which is airflow in a hospital room. This is a smaller version of that, which is airflow in an infant incubator. Okay, great. So here is the outline of my presentation. First, I'll talk about what is CFD when we say CFD and what are the benefits of the CFD. Then I'll talk about airflow pattern in a hospital room. Then I'll discuss thermal comfort of a patient and let's say staff and surgeon in a hospital room. How can we use CFD analysis and CFD results to evaluate thermal comfort of residents? I'll talk about airborne transmission, in other words, transmission of bacteria in a hospital room. And in the last session, we used CFD results to optimize the design of HVAC system in a hospital room. Okay, let me go to the next slide. So first, what is CFD and what are the benefits of CFD? CFD, when we are saying CFD, CFD refers to a computational, in other words, numerical method to solve flow problems. What the figures on the right, this figure is showing a hospital room where I have a block which represents a doctor and a block which represents a patient on a bed. I use block for the sake of analysis because it's easier to measure. Of course, you can put a real, like a man with hands and heads, but it won't change the result significantly. So this slide shows type of results that we get from CFD. The contour plots are temperature, so we can get temperature at every location, including over the body of the patient. The arrows are velocity. We can get magnitude of velocity and direction of the velocity. And this trajectory shows how bacteria are leaving the mouth due to coughing. So it shows trajectory of bacteria after a patient coughs in the hospital room. So the benefits of the CFD, we can get it from this figure, is that it gives you very detailed information. It is three-dimensional. It is steady and it can be transient. As I said, this is bacteria moving in time. So it can be transient. And the main advantage is that it is quick and not expensive. All you need to do the analysis is an engineer and a computer. Because of the advantage of that I mentioned, application of CFD in ventilation of healthcare has recently become very popular. It has attracted tremendous attraction recently. And if I want to go more to the detail, why is it attractive in healthcare? Because once you do a CFD, you will have airflow pattern inside the hospital room. Then let's look at this hospital room. We have some recirculation here. Air is moving up, moving down, there is a recirculation. You don't want to have recirculation zone in hospital because bacteria can get trapped and then stay in the room. So once you have airflow pattern, you can modify your design to get rid of this recirculation zone. You can save heating and cooling energy of a hospital room. I'll discuss those in the later slides, how with optimizing the design, we can reduce the cost of energy. You can also use the airflow pattern to eliminate distribution of bacteria in the hospital room. Again, we'll discuss that later. We can use CFD results to improve comfort level of patient and doctor. And finally, we can use CFD results to come up with a design, HVAC design, where we can quickly increase or decrease temperature in a hospital room or in an operation room. We will talk about all these issues in the next few slides. Okay. And these studies are specifically very important for operation rooms because operation rooms has their own requirements. Comfort level of patient and comfort of a patient and comfort of a surgeon is very critical in the operation room, and they have different comfort level because they have different clothing, they are doing different activity. Patient is just lying on a bed, surgeon is doing activity, so the comfort level is different and it needs to be addressed. Of course, control of concentration of pollutants of bacteria is very important in the hospital room. And in the hospital, in an operation room, also in operation room, we want to be able to quickly increase or decrease temperature without large overshoot. And finally, there is a requirement that the air velocity at the wound site should not be more than 0.2 meters per second. Otherwise, there would be excessive drying at the wound site. We can use CFD result to evaluate air velocity next to the wound site, and we'll discuss that more in detail in the next few slides. So let me go to the next slide. Okay, so for the next few slides, I am focusing on a geometry which represents a hospital room that I'm going to describe that geometry here. So this is a hospital room. I have a doctor and I have a patient, where patient is on a bed. Doctor and patient have a body heat flux of 60 watt per square meter. There is a medical equipment at the corner of the room with heat flux of 100 watt per square meter. The room has a lamp on the ceiling where it generates heat equivalent to 200 watt per square meter. And there is an inlet and outlet both at the ceiling where inlet temperature, the temperature of the air which is coming is 20 centigrade and the flow rate is 6 ACH. Outside temperature, like outside the room, outside the hospital, the temperature is 5 centigrade and there is a heat transfer between outside and the room through this wall and the ceiling, where we use materials of heat transfer coefficients of the, let's say, brick, cement to evaluate resistance of heat transfer resistance of wall and ceiling, and we use those numbers in our code, in our simulation. So this describes the geometry that we are going to discuss in the next few slides. Let me go to the next slide. So in the next few slides, I will discuss airflow pattern for this specific geometry. This figure shows a airflow field and temperature distribution across a section through the hospital room. So the contour plots represent temperature where it's between 19 and 24 centigrade, and the arrows are representing velocity. As you can see, there is a airflow coming from patient toward the doctor, and there are two recirculation zones here and here, which are not ideal because, again, bacteria could get trapped in the recirculation zone and it won't leave the hospital room. I mentioned in the previous slide, one of the previous slides, that in operation room, we want to have air velocity less than 0.2 meter next to the wound site. We can get that easily from our simulations. Let's assume that this is the operation room. So we can cut a section or put a section next to the patient and plot velocity next to the patient. So that's what I have done here. The color contours here represent magnitude of velocity next to the patient, and as you can see, the color is blue, so it's less than 0.1 meter per second. So I can conclude that if this was an operation room, then velocity next to the patient is less than 0.1 meter per second, and it satisfies the requirement for the operation room where velocity should be less than 0.2 meter per second. Okay. The next topic that I want to discuss is thermal comfort. Thermal comfort is a discussion by itself. It's a big topic that here I try to squeeze it in one slide because of the time limitation. I try to make it very clear, but my goal is that your take of this slide is that eventually you can use CFD results to evaluate thermal comfort. So in order to evaluate thermal comfort, you need some input, and those input you can get it from CFD analysis. Let me explain what thermal comfort is. Thermal comfort is a state of mind that expresses satisfaction with thermal environment. So if you are in a room and you were asked, how do you feel about this room? Give us a number based on this table. If it's cold, give us -3. If it's hot, give us 3. That number expresses thermal comfort. So thermal comfort, again, it's not related to the equation of heat and mass transfer or energy balance. It is just a state of mind. How do you feel about your environment? So now the question is, what is thermal comfort related to? Thermal comfort is related to how much clothing you have. Like, what is your, are you wearing a t-shirt or are you wearing a couple of layers of dress? So it depends on what's your clothing level. It depends on what's your activity level. Are you in a gym, or are you in a library, or are you in a hospital room sleeping on a bed? It depends on the humidity of the air. And it also depends on two parameters which we can get from CFD analysis. One is temperature around your body. The other one is air velocity that hits you. So, but how can we correlate these variables to the thermal comfort? What is done is that they have done many psychological experiments have been done where the goal was to make correlation between the variable that I just explained to the thermal comfort. So these are all experimental studies that people were asked to give a number between -3 to 3 based on how they feel, but the other parameters such as the level of clothing or the activity was known. So those correlations exist. And again, the input for those correlations, two of the inputs are air velocity around you and temperature around you. Those two numbers, we can get it very accurately from CFD analysis. And if I run thermal comfort analysis for this room, the number that I get from this room is -1.6. It means that the room is cold. And there are some other equations that I didn't put it that can be converted that 56% of patients in this room are feeling cold. So the design is not a good design, and we need to optimize this design. All right, so this is all I had to say for the thermal comfort, but the main point is that we need some information from CFD analysis to have thermal comfort which is specific to each person, because let me go back actually a couple of slides. Because temperature of a patient and temperature of doctor is different. You cannot use one temperature to represent what doctor and patients are feeling. So we can use CFD analysis to evaluate thermal comfort of patient and doctor individually. Okay. The next topic that I want to talk about is airborne transmission of bacteria. Example of the threat of airborne transmission of bacteria is swine flu pandemic in 2009. So airborne transmission is very important, especially in hospital rooms. And here, in this analysis, we just focus on airborne transmission due to coughing. Once you cough, large droplets fall on the floor. A small droplet become aerosolized, and they start to move in the air because of the airflow around you. So since we are doing fluid flow analysis, we need some information to simulate this coughing. I use a study which is done, which I have cited here for your reference, that shows what is the cough flow rate in vertical axis versus time in horizontal axis. So I know the cough flow rate, what is the flow rate due to the coughing, and I can use this information for my simulation. Let me go to the next slide. Okay, this slide shows trajectory of particles of bacteria due to coughing. Here we assume that bacterial particles are released for a coughing duration which is 0.5 seconds. And if you follow trajectory of particles, you can see that at about 30 seconds, most of the particles, bacteria, are leaving the room, whereas the rest of them are staying in the room, and eventually because of the local turbulences in the room, they are covering the entire room. And basically they are contaminating the entire room. And this is not of course ideal. So let me Let me be more precise about what's happening. Here I'm showing probability of bacteria removing the hospital room versus time. So at about 30 seconds, 90% of bacteria are removing the hospital room. But if we progress in time, we see that even after 360 seconds or 300 seconds, still 8% of the bacteria are in the room and our ventilation system could not take them out. So they're staying in the room. Okay, so these are all good informations. Like we can detect airflow pattern, we can detect recirculation zones in a hospital room. We can follow trajectory of bacteria, see how long it takes them to leave the hospital room and how much of them are not leaving the room. And we notice that there are some flaw in the current design that we have. Now the question is that how can we use this information to optimize the design? How can we get rid of the recirculation zone? How can we remove bacteria faster? Or the room was cold, how can we increase temperature of the room without using more energy? This is where design optimization comes to the question. And usually what we do is that engineers look at the results and look at the results of the baseline design, and they look at the flow patterns, they look at trajectory of particles, and they come up with some design modifications. Here, I narrowed down the design modification just to moving the location of outlet. So if you remember, outlet here is pink. In the baseline design, I had inlet at the ceiling and outlet at the ceiling. In the design number 1, I moved outlet from ceiling to the wall above the patient. In design number 2, I moved outlet to the wall opposite to the patient. And in design number 3, I bring down the outlet. So again, that there are many things that we can modify. We can change arrangement of, let's say, patient, wardrobe, or equipment. We can change locations of the outlet, inlet, outlet, or we can change the flow rate. But here we just limited ourselves to the location of the outlet, and we came up with 4 different designs. For these 4 different designs, I'm going to compare airflow patterns between these 4 designs for you. Then I will compare average temperature of the rooms between these 4 designs to see if we could improve the temperature and make it warmer. And finally, we'll compare efficiency in removing bacteria between these 4 designs. Okay, so let me go to first airflow pattern. Here I'm showing airflow pattern across the same section in all 4 designs, but I am rotating design 1, 2, and 3 with respect to the baselines. They are not all at the same angle because I wanted for you to also see that where the outlet is located. But these cuts are all at the same sections. So if you remember, in the baseline design, we had 2 big recirculation here and here, where in design 1, we could get rid of those recirculation, but now we have another recirculation right above the patient. Design number 2 is, we don't have those recirculation, we just have minor recirculation in front of the wardrobe. And in design number 3, we have the same recirculation here and another recirculation next to the doctor. So you see that we could eliminate some of these recirculation, we could move them to different locations, and we can do further analysis to see how much is the strength of these recirculations. Probably you run some numbers, you see that these, let's say, the strength of this recirculation is not significant, and you can ignore it. So that's the airflow pattern. In the next slide, I'm comparing average temperature between these 4 designs. So baseline the baseline model had average temperature of almost 21, whereas the design 1 and 2 and 3, the average temperature is about 25 in all three. It means that we didn't change flow rate, we didn't change temperature of the air which is coming to the hospital room. By just changing the location, moving the location of outlet, we could increase average temperature of the room so that the patient would not be cold. So in other words, energy efficiency was improved. And the next topic that I want to discuss is now between these four designs, which of them is the most efficient one in removing bacteria. If you remember, this is baseline design, but some of the bacteria, about 90 or 92% of them, left the room at about 30 seconds. The rest start to move around, and eventually, because of the turbulence, they covered the entire room. However, if we look at design number 1, where the outlet was, let me go back to design number 1. This is design number 1, where I put the outlet right above the patient on the wall. If you look at design number 1, at about 15 seconds, all the bacteria are sucked out and nothing is remaining in the room. So, like, we can say that design number 1 is significantly better if the focus is just removing bacteria. In the next slide, I compare these four designs in terms of efficiency in removing bacteria. Again, this graph, horizontal axis is time, vertical axis is probability of removing bacteria. Design number 1, which is blue, at about 15 seconds, 100% of bacteria are removed from the system, from the hospital room. Where in our baseline design, at about 30 seconds, 90% was removed and the rest stayed in the room and eventually covered the entire room. So this is baseline design, design number 1. Design 2 and 3, these two designs are not doing a good job in terms of removing bacteria. Especially design number 3, as you can see, it just starts to remove bacteria at about 250 seconds, and even then it's not doing a good job. After 260 seconds, 30% of bacteria are left the room, and still we have 70% of the bacteria in the room. So if our goal was just to come up with the best design to remove bacteria efficiently, then design number 1 wins here. And here I conclude my presentation that CFD, which is a numerical approach to solve flow field, gives us capability to optimize airflow system in a hospital room or operation room. By doing that, we can save energy, like heating energy and cooling energy. We can reduce the possibility of contamination due to bacteria, flow of bacteria in the air. We can also get rid of recirculation zone. Basically, CFD provides us a powerful tool of having airflow pattern where engineer, by looking at airflow pattern, can come up with a better design. And that is it. Thanks a lot for listening to me. Milad?
Alreza, sorry, I had to unmute myself. Thank you very much for that great presentation.
Sure.
And just 1 second. Yes, and in the case you guys have questions, now it's the time. Just enter them into the question toolbox, and Alireza and me will try to answer all of them. And in the case you got a question later, you can also reach out to us using email. All right, it seems like all questions were answered. Oh, there's a question by Ricardo Salazar, and I think it's related to Alireza. And Ricardo wants to know if there is any CO2 standard for hospital ventilation and thermal comfort inside hospital rooms.
And yes, there are actually. I know American standards because I work with American clients, but I put it in the presentation. Like, if you follow this code, ASHRAE standard 55, it gives you a guideline.
Yeah, and just to add something, as far as I know, also in Europe, basically the ASHRAE 55 standard was just adapted.
Okay, very good. But if so his question was more about like design code, right? It was not about simulation.
No, building codes. Like the ASHRAE code was copied by the European. So the European DIN code is basically also the ASHRAE 55 code.
All right, great.
Or the green building codes, for example, are also based on that.
I see.
And then there is a question related to SimScale by Suda. And he wants to know regarding natural ventilation, when you add with louvers, how do you define in SimScale? Yes, usually what you do, Suda, is that you would include the body of your outlets or your louvers into the CAD model, and then you would yes, add it as an obstruction or add any slot of the louver as a single inlet. So basically you use your CAD model to add it. I don't know if there are other possibilities, but I think that should be pretty straightforward. All right. There's a final question by Yves. He wants to know what are the optimizing capabilities with SimScale. So SimScale itself does not have any optimization code. So you can run the simulations, but if you want to modify the geometry, you have to do it manually. But we also have some partners like the company cases with their with the software cases, which you can directly connect to SimScale, and which will help you to do automatic degree of freedom studies, optimization studies. Yes, Zahil wants to know, and I think this question is again related to Ali Reza, how much time did you spend to create the simulation and verifying the results?
So this approach to all type of all simulations, not just this simulation. So the consuming part is to set up a model. Once I set up the model, once you have a model which is running, the rest, which is optimizing, let's say, modifying the model, putting out a different location, is very quick. So in this case, let's say in this model, probably it took me 1 or 2 days to set up the model, but then the other analysis having out at a different location is what it was just a matter of couple of clicks, have a different run, let it run, let the computer do the job.
All right, thanks Ali Reza for that, and there are some other questions that are coming in, so let's do 3 or 4 other questions. And Mustafa wants to know or ask that this is a demo, and how much more work it is if you want to, or how much more difficult it is if you want to run a simulation of a whole building with many rooms, or if you have larger facilities you want to simulate.
The concept is the same. It doesn't matter if you have 1 room or 2 rooms connected together, or you have the entire building. The concept is the same. The only thing which is different is the computational power. So you will, if you have some difficulty, you increase number of CPUs or you run on a cloud. But the concept, the mathematical equation, everything behind it is the same.
Yeah, and I think you should also consider that there won't be a lot of applications where it's necessary to simulate all rooms. Usually you try to make your problem as small as possible and try to isolate only that rooms or that part of the building which are relevant to your problem.
Yeah, that's a very good point. So for hospital room, that's usually the case. We look at the hospital room, we look at the operation room. It's just 1 room. But if you want to look at, let's say, theater or a shopping mall, then the problem is has different scale. So the sizes are bigger, but still same approach.
All right. It seems like we answered all of the questions. Alireza, again, thank you very much for being here with us, and it was a great pleasure for us.
Same here.
And just for those of you who've asked, we will provide you with a recording of the webinar. We will send it to you by mail tomorrow or the day after tomorrow, and there we will also include the contact details of Alireza in the case you have questions or you're looking for a consulting partner who can help you to work on a project. Yes, also thank you very much for joining today, and hope to see you soon again. Have a nice weekend, and yes, see you soon. Bye.
Thank you. Bye.